If you ever tried reading about quantum mechanics, then there is a possibility you come across some strange ideas, such that an electron can be at two places at the same time, or that there's a parallel world where a copy of you exists. So, how do we get to the point where we allow ourselves to imagine such ideas? When it comes to quantum mechanics, we can say that physicists found themselves in an unexpected scenario where they had a coherent and experimentally supported mathematical work, but they had no certain conceptual foundation for it. To begin with, it seems it's all about how we define and perceive these very basic concepts that are energy, matter, waves, and particles. Let's talk a little about these. Matter is the name that we ascribe to things that we can touch, that we can squeeze, that we can move around, and particles are the smaller units that make up matter. So, what about waves and energy? Here's a very mundane scene of daily life. A water drop disturbs the surface of water, and this disturbance propagates through space, resulting in these circular waves traveling away from where the water drop fell. We explain this traveling disturbance by saying that energy propagated through the oscillations of water particles. So water particles themselves were not displaced, but it's energy that propagated. So energy, unlike matter, is something very abstract. We do not acknowledge its presence directly. We rather acknowledge the change in it, or as demonstrated in this example, the transfer of it, in the form of a wave, for instance. Physicists had always considered matter and energy to be separate and distinct entities, and waves and particles as separate models. So the conceptual troubles start when these concepts begin to overlap, when they start borrowing each other's characteristics, which is something that started to happen by the beginning of the 20th century, when scientists tried to solve problems like the black body radiation and the photoelectric effect. This is when they had to think beyond the framework of classical physics. Now, to solve the first problem, Max Planck assumed that energy was quantized, which is one of the most insane ideas. That means energy only occurs in certain values that are the multiple of a certain integer, which is now known as the Planck's constant. And then Einstein used Planck's idea and assumed that light was quantized, actually made of particles, that was later given the name photons. And we could calculate the momentum of these photons using this equation. The game has changed pretty much by now, right? This particle-like nature of light was later generalized by de Broglie hypothesis. Not only waves could exhibit particle-like features, but particles, like electrons, could also exhibit wave-like features. And this could be expressed by rearranging the previous equation so we can solve for the wavelength. So now we can get the wavelength of an electron? Great! But if an electron has a wavelength, does this mean we're talking about an electron wave? Is there such thing? And how do we conceptualize it? Can we think of an electron wave in the same sense we think of a water wave? Well, Erwin Schrödinger was the one to make progress from this point. This is his contribution, and this is psi, the function that describes the shape of the wave we're talking about. So now we can solve this equation for psi, plot a graph of this wave, and have a mathematical representation of it. But how do we interpret this? Once again, what is this wave? Surprisingly, there's no agreement upon the answer to that, but Max Born suggested something that we pretty much hold for now. This function represents the probability of finding the electron at a particular place. So where there's a high value of psi, there's a high probability of finding the electron, and vice versa. Born's idea proves to be reliable, but still the nature of this wave function remains mysterious. We still don't know what it is. Is it just a mathematical tool that reflects the limitation in our knowledge of reality? Or is it a reality in itself, like a representation of a real physical object? And in this case, the electron is at all the possible places until you look for it. So does the measurement of the electron determine its position? Is reality subjective? All of these questions remain unanswered, but the bright side is we could change the world drastically with the applications of quantum mechanics.